I am Dr. Sonia Kundu, Associate Professor in the Department of Basic Science and Humanities, University of Engineering and Management, Kolkata. I'll be speaking on heterocyclic compounds with special reference to furan.
Now I have divided this topic in 3 modules. Module 1 is the introduction, where I'll be speaking in general about what are heterocyclic compounds, and then module 1 consisting of the second chapter, which is nomenclature and classification. How do we name the heterocyclic compounds? What are the various classifications of heterocyclic compounds? Module 2, I'll be concentrating on furan, its structures and some general properties, and what are some generalized synthesis of producing furan. Module 3, I'll be concentrating on different reactions of furan like nitration, chlorination, sulfonation, hydrogenation, etc. Certain furan derivatives, are furan derivatives useful? And also what are the medicinal aspects or the medicinal applications of furan. Now coming to the first chapter of module 1, which is introduction. So basically what are heterocyclic compounds? These are cyclic compounds with the ring containing carbon and other elements, the commonest being oxygen, nitrogen, etc. It consists of 5 or 6 membered heterocyclic rings. It can start from 3 and go to 10 number of rings also, which are stable with conjugated double bonds and possess aromatic characters. There are certain heterocyclic rings like ethylene oxide which can easily be reopened, and they do not possess any aromatic character, hence they are not considered as true heterocyclic compounds. Now coming to the second chapter of the module 1 is nomenclature and classification. Now to begin with nomenclature, how do we name these heterocyclic compounds? The names of the monocyclic compounds are derived by prefix indicating the nature of the heteroatom present and eliding A wherever necessary, like for oxygen we say it oxa, for sulfur it is thia, and for nitrogen it is aza. Now when 2 or more of the same heteroatoms are present, the prefixes di, tri, etc. are used, like dioxa, triaza, etc. Now if the heteroatoms are different but present in the same ring, so how do I name them sequentially, or what should be the naming order? So their order of citation starts with the heteroatom of as high a group in the periodic table and as low of atomic number in that group. So say a ring consists of oxygen, sulfur and nitrogen at the same time. Okay, so how do I name them first? Now what happens? Oxygen and sulfur occur in the same group in the periodic table, but nitrogen is not in the same group. It is a group below that of oxygen and sulfur. So one thing is clear, oxygen and sulfur will be named first because high a group in the periodic table than nitrogen. Now amongst oxygen and sulfur, which will come first? Of course oxygen will come first because the rule says of the same group but of low atomic number. So oxygen has low atomic number, so the order will be first oxygen, then sulfur, then nitrogen. Now if there were other heteroatoms like phosphorus and silicon, then the full order will be oxygen, sulfur, nitrogen, phosphorus, silicon. Now say if a ring consists sulfur and nitrogen, then how will I represent it? It will be known as thiaza. First sulfur and then nitrogen. Okay, now the size of the monocyclic ring can be from 3 to 10 and it is indicated by a stem. Say 3 ring, then it will be 4 et, 5 all, 6 in, 7 ep, 8 oc, 9 on, 10 ek. Now the fifth point is, now if there are your unsaturation present or saturation is present, now the state of hydrogenation is indicated in the suffix, like for a 3 ring unsaturated compound with N atom or the nitrogen atom, the name is irene, whereas for Saturated one, it is iridine. It is also given as prefixes like dihydro, tetrahydro, or by prefixing the name of the parent's unsaturated compound with the symbol H preceded by a number indicating the position of saturation. Like here you can see in the 2 position NH and in the 6 position there is saturation present. So 2H, 6H, 152 dithiazine. Clear? Now, in a monocyclic compound containing only one heteroatom, the numbering will be starting at that particular atom. But the ring, when it is numbered such that the substituents or heteroatoms are given the lowest numbers possible. Now, if the heteroatom are different, the numbering starts at the atom cited first according to the rule 3 that we have seen previously and proceeds round the ring in order of precedence. Now coming to the classification, heterocyclic compounds can begin from 3-membered and it can extend up to 10-membered ring. I have just shown some examples of 3-membered, 4-membered, 5-membered, 6-membered and 7-membered ring. Now following the nomenclature, in case of a 3-membered ring, remember it was was there. So when it is N, so it will be what? N means my as I said. So in their first compound, we see that it is a saturated compound. So it is aziridine, IR. And for the unsaturation present, it is azirine. Now a 4-membered compound, it is azitidine, it is azit. Unsaturation when it is present, it is 5-member, it is pyrrole, and in case of saturation, it is pyrrolidine. For 6-membered, it is piperidine and pyridine, and for 7-membered, it is azipane and it is azipine. Clear? And for 8, 9, it will be so on. Now coming to the second module, the first chapter is furan, the structure and properties. Now furan, also known as furfuran, it consists of 4 carbon atoms and 1 oxygen atom in its ring as shown in the structure. Now there are 2 monosubstituted derivative and 4 disubstituted derivatives possible in case of furan. It has a resonance energy of 71.1 to 96.2 kilojoule per moles. It is best represented as a combination of 5 resonance hybrid structures as is shown in the figure. So here as we can say that as it is a conjugated diene, and you can see in the figure I can show that 5 resonance hybrid structures are possible. So I can say that it possesses aromatic character. Now all the atoms in the furan ring are sp2 hybridized. As sp2 hybridization is planar, furan ring is essentially planar. The essential criteria for a molecule to be aromatic is a monocyclic molecule must be planar containing 4n plus 2 number of pi electrons. In furans, the total number of non-bonding electrons is 6, 4 from 4 carbon atoms and 2 of 1 oxygen atom. So furan is essentially aromatic. Now the ring current of furan is seen to be less than that of benzene as evaluated from the NMR data. Hence furan has less aromatic character than benzene. Now we are coming to the next chapter, which is furan synthesis. Now furan is obtained when wood, especially pine wood, is distilled. It may be prepared by the distillation of mucic acid and heating the product furoic acid at its boiling point. So according to the reaction, we see mucic acid is heated, is dry distilled to give my furoic acid, which is 2 carboxylic furan acid derivative and carbon dioxide and water, and when this Furoic acid is heated at its boiling point. It decarboxylates to form furan. It may be manufactured by the catalytic decomposition of furfural in steam in the presence of an oxide catalyst. So with the aldehyde derivative or furfural, it can be catalytically decomposed with the presence of an oxide catalyst to furan. A general method of preparing furan derivatives is to dehydrate 1,4-diketones or dialdehydes as shown in the figure with phosphorus pentoxide or sulfuric acid, etc., where the water molecule dehydrates to give a cyclic ring of furan. And also furan derivatives can be prepared by the Feist-Benary synthesis, where an alpha chloroketone is condensed with a beta ketoester in the presence of pyridine. As an aromatic compound, but in some ways it behaves as a 1,3-diene, thus it undergoes Diels-Alder reaction to form an adduct as shown in the figure. Furan is catalytically reduced with ranitidine or palladium oxide to give the saturated compound tetrahydrofuran. Coming to the substitution reactions in furan, what it is seen that the canonical structures which carry unlike charges are less stable than the uncharged structures, and larger the charge separation, the less stable the structure is. So uncharged furan is much more stable than the other 4 canonical structures. Also from the resonance structures it is observed that the electron density is higher at position 2 and 5 rather than at position 3 or 4. So on the basis of charge distribution, electrophilic substitution would be expected to occur at position 2 or 5. Again, alternatively, if we consider the contributing resonating structures of the intermediate carbonium ion, then there are 3 for 2 and 2 for 3 substitution. So the first, in the given figure, the first diagram represents substitution at 2 position, where we see that there are 3 contributing structures, and the second one is at attack of the electrophile at the 3 position, where we can see contributing structures are 2. So my 2 position electrophilic substitution will be much more prone than my 3 position electrophilic substitution. Now furan is readily polymerized by concentrated acids, hence nitration with mixed acid and sulfonation results in resinified products. True nitrofuran may be prepared by nitrating furan with acetyl nitrate, and 2-sulfonic acid may be prepared by the action of pyridine sulfur trioxide on furan. Furan reacts readily with halogens, but the liberated halogen acid can polymerize the furan, same problem. So chlorination of furan, however, can be carried out at minus 40 degrees centigrade, which gives the 2-chloro and 2,5-dichlorofuran. Halogenated furans are sometimes prepared by indirect methods, as for example by brominating furoic acid and decarboxylating the product 5-bromofuroic acid to 2-bromofuran by heating in quinoline in the presence of copper powder, as given in the reaction. Alkylation reactions in furan leads to polymerization, but acylation with acid chlorides and anhydrides with tin chloride as catalyst gives 2 acyl derivatives. A better catalyst for the reaction is boron trifluoride and ether. Furan is very readily mercurated at the 2 position when heated with mercurous chloride and aqueous sodium acetate to give 2-chloro mercury furan. Since the mercury group is easily replaced by bromine or iodine or the acyl group, these mercury compounds are useful intermediates. The reaction is given in the figure. Furan also undergoes Gattermann reaction to form furfuraldehyde, that is, furan when treated with carbon monoxide in the presence of aluminium trichloride and HCl, it gives furfuraldehyde. And butyllithium to form 2-lithium derivative, which behaves like usual organolithium compound and gives fluoric acid with carbon dioxide. Pyrols are sometimes prepared commercially from furans by treating it with ammonia in alumina catalyst at high temperatures. Now coming to the furan derivatives, the first one is furfural. Now the structure of furfural, better known as furfuraldehyde, is shown in the figure. It may be prepared by distilling pentoses with dilute sulfuric acid. Furfural is chemically similar to benzaldehyde, as for example, with aqueous sodium hydroxide, furfural forms furfuryl alcohol and fluoric acid by the typical Cannizzaro reaction. Next, with ethanolic KCN, furoin is formed, which is the benzoin condensation, and this on oxidation gives fural. When heated with aqueous KOH, fural gives furulic acid, which is the benzylic acid rearrangement. Furfural condenses with dimethyl aniline in the presence of zinc chloride to give furfuraldehyde green, which is a characteristic reaction of furfural, is the red color it gives aniline. Now we come to furan derivatives, fluoric acid. Structure of fluoric acid is given in the figure. Now fluoric acid may be prepared by dry distillation of mucic acid or by the oxidation of furfural with cuprous oxide or silver oxide in aqueous NaOH. Fluoric acid behaves much more like the aliphatic acid rather than benzoic acid. As for example, it is readily oxidized by alkaline potassium permanganate, brominated by bromine vapor and oxidized by bromine water to fumaric acid. Nitration with mixed acids, fluoric acid gives first the 2-nitro derivative and then the 2,5-dinitropfuran. Now we are coming to the last chapter of module 3, the medicinal applications of furan. Furosemide is an important class of diuretics and it is a furan derivative. Furosemide is essentially used for the treatment of edema associated with renal disease, nephrotic syndrome, cirrhosis of the liver, and also against congestive heart failure. It may also be employed for the management of hypertension. Next is ranitidine, which is a very important antihistaminic agent and also a very common drug which is widely used for the treatment of duodenal and gastric ulcer, is essentially also a furan derivative. There are other also important drugs which essentially consists of the furan derivative and has high medicinal implications. With this, I come to the end of the discussion on heterocyclic compounds with respect to furan. I have talked about what are heterocyclic compounds, the nomenclature and classification of the same. Then I have focused on furan, on its generalized synthesis, the structure and properties of furan. I have tried to cover on the different reactions on furan like substitution reactions, then hydrogenation reactions, Diels-Alder type of reaction. I have also gone through some of the furan derivatives like furfuraldehyde, fluoric acid, and also lastly the medicinal implications of furan and furan derivatives. I hope that this presentation will be really helpful from the heterocyclic chemistry point of view and also for the pharmaceutical students. Thank you.